In this video, we are going to address two questions for assignment number 3. In the first question, we're going to concern ourselves with the overall displacement of a bar with multiple sections where there are 3 externally applied forces. So we have F1, F2, and F3 being applied at different locations along a bar with 3 sections. In the second question, we're going to look at the same system with 3 sections, same bar, and instead we're going to ask ourselves and answer the question of what is the elongation of the middle section, so this section between forces F1 and F2. Well, let's go ahead and get started on the first question. And for this problem, we're going to use superposition. So you can watch the video from the class about how to use superposition to get kind of a general idea. Nonetheless, and we're going to solve the same problem, essentially, that's given in example 3.4, and we're going to answer the questions that we have here. So what we have are F1, F2, and F3 being applied, and using superposition, we know that we can think of displacements due to each one of these individually applied loads or forces, and then add those individual displacements to each other to get the overall displacement, delta, at the right side of the system. So let's go ahead and start to break down the problem by looking at the resulting displacements at the right end due to these individual applied loads. So we draw out the bar again, and in this case, we're just going to look at the resulting force at the right side due to F1. So here's F1 and here's the delta 1. And in order to understand what this delta 1 is, we need to know what the internal forces in the various sections might be and figure out what the deformations of those sections are and then get to delta 1. So if we look at the left section that we have here and we draw it out, we see that we have a reaction force F1, okay, on the left side. There's only one external force. So if we do external equilibrium for first, there's going to be reaction force F1 on the left side. And then we take a slice like that, and we see that open face, and F1 has to be, or the internal force has to be equal to F1. F1 equals F1. So now we know what the internal load is in section 1. What about what's happening, say, on the right side? Well, on the right side, we have 0 applied force here, 0 applied force here, quite frankly. And if we do a section, so we cut this here and we keep the right side. So this is 0 forces, maybe being applied at the end. So 0 force. The internal force is going to be 0 as well. And if we look at the middle section, we see that there is, well, going to be 0 force being applied here from the right side. And if we take a section and we cover up the left-hand side here, what we get is, well, again, equilibrium of 0 force and 0 force. So at this point, what we see is there is only an internal force in the first region of the bar. And the displacement at the right side is going to be equal to the displacement associated with this first section. So that might be a little bit counterintuitive, but one thing we can think is that, well, there's no force here, there's no force here. These two right sections are just along for the ride. They're just going to follow the displacement of this spring or this beam on the left, or this bar on the left. And they're just going to keep going with it. And so whatever displacement we have here is the displacement we're going to have at the right side. So delta 1. So what is the displacement, though, of this section on the left? Well, it's just the internal force divided by K1, right? K1 delta is equal to force. So the internal force dictates what this displacement is going to be. So that's solving for the contribution of F1. Let's now look at the contribution of F2 to our overall delta, and we're going to call the displacement on the right side due to F2, we're going to call that, as you're going to guess in a second, we're going to call that delta 2. Right? So here's our delta 2, and here's our F2. Okay? And notice F1 is not applied to the system. We're just looking at the resulting displacement because of F2. And now we do the same procedure to look at what the internal forces are in various sections of our bar. And we have gone a little bit faster than maybe we did in the first session or second session, but what we have is external equilibrium dictating that there's going to be a force from the ball acting on the 3-section bar, and that force is going to be balancing this F2. So we have an F2 acting to the right, which means that internally when we take a slice right down there, and I can, what I'm talking about when I say these slices, right? Take a slice right down there, and then that's the exposed right side of this leftermost section. We have an internal F2 that has to be counteracting the F2 in order for that to be in equilibrium. Now, what happens in the middle section? Well, we have this external force F2, okay, and then we take another slice, and we see that when we expose that left portion of this middle section, we have an F2 that's balancing that F2. And when we go to the right side, well, if I see that, again, there's no force applied on the right side of this, there's a 0 force, and I take a slice like this, then I'm going to have an also 0 force internally. So there's 0 force internally on this member. There is the F2 applied on this member, and there's the F2 applied to this member as well. And we have spring constants associated with the middle and the left region, and there are K1 and K2. And there may be a couple of different ways to look at this. One way, though, is to say that we're going to assign an effective spring constant for this two region, or this region and this region, for the entire bar. And we're going to think of, okay, I'm applying an F2 that's going to be putting these two regions under compression. So K effective, these are springs acting in series, is going to be K1, K2 over quantity K1 plus K2. And look, F2 is acting in the opposite direction of delta 2, which means that this compressed region, or two region, the region 1 and region 2 that are being compressed, that's going to be going in the opposite direction that we've defined our delta 2. So now we add a negative sign, and once again we know that we have a force divided by displacement, so we have force divided by a spring constant, which gives us a displacement. So we have our negative F2 divided by the K effective is going to be equal to delta 2. Okay. Now, what about the third contributor to this system? We can write it out as follows. And so the other way, yes, so the other way to think about the displacement delta 2 is to say that we have a delta here and a delta here, and we can calculate each one of those deltas based on the internal force F2, and that's what you see here, so minus F2 over K1 plus minus F2 over K2, and so this is exactly the same expression for delta 2. Okay, moving on to the third, what we have here, again, is a representation for the displacement of the right side. We'll call that delta 3, and that's going to be due to our third force. And again, F1 and F2 are not acting in this system. We're looking just at the delta 3 due to F3. And this one might be the simplest if you just want to go ahead and say, okay, what's the effective spring constant for this entire beam? And then I apply F3 divided by that spring constant. But nonetheless, let's go through the exercise of looking at the internal forces. We have a reaction force F3 on the left side that's going to be pulling that direction, opposite of F3. So that's this force right here. Then if we take a slice right here, whoops, that was a weird looking slice, I guess. If we take a slice right here, okay, we have this F3 like that. And we also have equilibrium with F3 in the middle section, and we have equilibrium with F3 in the right section, following similar procedures that we've described previously using method of slices. And let's go ahead and figure out what the effective spring coefficient is for the entire three-sectioned system. And that effective spring constant, or spring rate, or spring coefficient can be considered to be equal to, or the reciprocal of it can be equal to 1 over k1 plus 1 over k2 plus 1 over k3. And so we can figure out what delta 3 is by simply taking, again, the force divided by the spring constant, or force times 1 over k equivalent, and we'll get our delta 3 here. So now the overall delta is just going to be delta 1 plus delta 2 plus delta 3. And so we have delta is equal to delta 1 plus delta 2 plus delta 3, and we can write it out as we see here. So this is the symbolic algebraic representation for what the overall displacement is. And this will answer, sorry, if we go back, I guess there was a lot of stuff here that we just did. That is the first question that we're interested in answering. The second question is, what is the elongation or the deformation of this middle region? And we're going to, again, get a displacement in units of microns for that. Now, so how do we approach this one? Well, what we really want to understand is, what are the contributing factors to the internal force that is in the middle region? And once we know that force, the internal force, well, we can just use the information we have for the spring coefficient and understand that the internal force divided by the spring constant is going to be equal to the displacement or the deformation of just that middle region. Okay, so how do we figure out what the internal force is? Well, we can once again use method of sections, and this time we're going to take a slice down the middle and expose the left side. So we have an external force F2 right here, and we have an external force F3 on the right side. And this internal force Fi has to be in equilibrium for this system. So we have F3 minus F2 minus Fi. Fi is an internal force. It's going to be F3 minus F2. And we can say that our constituent relationship of F equals K delta is still valid. And so it's going to be this F internal divided by the spring constant, K2 is equal to delta 2. And that's all we have to do for the displacement in the middle. Once again, there is a way of implementing the algebra in Colab. And we're not going to deal with the symbolic representation as we did previously. And we're also not really going to even spend time doing the writing of the script. I'll just show you that it is available for anyone who's interested here in this Colab script. Once again, we'll go ahead and make sure we enable the first cell, which allows us to have the NumPy library active. And then we go down and we see that there are examples for 3, 4, and let's see, yeah, this is 3, 4. Okay, I guess I didn't include the internal one. Okay, well, you can, that one's not too bad, but if we just run this, and you can put in different values for k, for forces, K's and forces, and you can get the overall displacement here. So we run this, and for this particular system where we have a spring constant of 200 kilonewtons per millimeter, and that's been converted over to newtons per meter, so you multiply by a million, or 1e6, right? And that's for the three spring constants, and then we have the three forces, F1, F2, F3, and then we can calculate the overall delta as we see here. Okay. Thank you for tuning in, and I hope you found this information helpful.